Really excited to introduce our key members of the Arizona Geological Survey team. I'm delighted to work for us. Brian Gootee and Carson Richardson. Carson's actually going to go first in the talk, but Brian's alphabetically first, so. So Brian's a senior research scientist. He's in charge of our subsurface basin analysis group, which is doing some really exciting work. And of course, we'll talk about some basin analysis in Big Sandy because the exposures are so great. He's been at the Arizona Geological Survey since 2007. He's done a whole bunch of different things, has many publications and maps. He's really a wonderful person to work with, so we're really delighted to have him here. He got his BS and MS from ASU, but we hired him anyway. So he's a native of Texas, and he has a lovely wife and 2 entertaining and charming children. Yeah? Okay. Okay, thank you. And then Carson. Carson is in charge of he's in charge of a lot of the survey, really. He's in charge of our mineral resources efforts, and he also has coordinated, for the past several years, our geologic mapping program. So it's really a big part of the survey. And he started with us in January 2019. He grew up in Indiana and fled as soon as he could, right? He's not looked back from that, yeah. He got his undergrad at Ball State, and he got his master's and PhD here at the U of A in geosciences. He's got lots of different interests in economic geology, obviously structural geology and regional tectonics, that sort of stuff. So really, we're delighted to have him. He spends his spare time keeping his poultry, chickens. No? Oh, no more poultry for Carson. And so anyway, I'll get out of the way. They can go. So delighted to have him here.
So you get me for the first third or so, and we'll see how the timing goes. So before we go into the actual details, no one works in a vacuum. This really builds upon significant labor that was done over the last 4 years at AZGS by almost every single person on staff. In addition to our staff, who we mapped, I think it's 13 plus quads through this area right now, we have additional collaborations with people in geosciences, such as Hervé Rizzo and his grad students, Tim Marsh and Bell Copper, geologists at Broadahead, Brendan Fernity and Joey Wilkins, and working with people at NAU on reprocessing legacy seismic data. We've also talked with many other people. I apologize for not listing you, but we're running out of space. And this has been heavily subsidized by the USGS's state map, EarthMRI, and one EdMap award to Hervé Rizzo. So broadly, I'll start out with the setting, context, motivation, and then talk about the magmatism and structure. And then Brian will take us 3 through 5. Oh, I should probably. And then at the bottom here, let's see if I can make this work. So basic chronology of events here. We have all the Proterozoic geology going down here, which people like Calvin and Chong care about. Then we go to the Laramide magmatism, episodes of erosion, and then the bulk of the talk will really focus on what's happened since the Miocene through the present. So here we are in northwestern Arizona. So the rightmost figure is showing, broadly the core complex belt, transition zone. And then this middle figure is a simplification of the state geological map with basically the broad distributions of the major rock types we've mapped in Big Sandy Valley. So the green is the deformed older Tule wash sediments. And above that, we have the undeformed Big Sandy Formation. So roughly Miocene for Tule wash, and then latest Miocene to Pliocene for Big Sandy. And then in terms of where we're going to be talking about today, here's an aerial image of Big Sandy Valley. On the eastern side, you have the Aquarius Mountains. The western side, you have the Wallapai. And then if you move north to south, we'll talk about 3 plutons, Wheeler Wash, Diamond Joe, Wickiup, and we'll briefly mention the Potier Range and Kaiser Spring volcanic field as well. So there's a number of Laramide plutons and porphyry occurrences up here. And the ones we'll talk about really will be Wheeler Wash and its possible prospect coming off it, Cava, or now Perseverance, Diamond Joe and the Big Sandy. And then we'll also talk about the former Devil's Canyon or Shannon Basin Pluton, and then the Wickiup Queen Banagas. And the critical thing to take away from all this is the fact that for several decades now, we've known that there is a largely hidden low-angle normal fault out here that was imaged in seismic in the early 70s or 80s by a shell. And that's this line here at the very top of the figure. This line here, this seismic reflection profile at the bottom, you can see this same fault image where it has about a 15 or 20 degree dip moving down to the east with synthetic faults and back-tilted strata in its hanging wall. Most of the plutons in the Wallapai range, which has most of the Cretaceous, there's very little Cretaceous in the Aquarius, they're typically bog standard granodiorites to quartz monzonites, nothing too really exciting or different chemically for them. Some of these ones that are plotting far off from these major fields, it's likely because they're least altered samples, and so you're having some sort of contamination with them. So starting north and moving south, the Wheeler Wash Pluton is a biotite bearing quartz monzonite to granodiorite. It has a significant hydrothermal alteration footprint in the northern Wallapais. So this is a topo quad map underneath there. Each of these boxes are 1 mile. So you're seeing a pyrite halo that is more than 4 miles in north to south extent here. The greens are areas of potassic alteration defined by quartz sulfide veins with K-spar envelopes and locally shreddy biotite with anhydrite. Those are associated with 3 of the 4 sericitic centers. And we also have in the blue areas of known coarse muscovite alteration. This pattern here has been very suggestive of a lot of fluids moving through these rocks and is what, combined with the seismic data, inspired Bell Copper to be looking for the faulted off top of this system here. And that is Perseverance, but we'll talk mostly about Diamond Joe and Big Sandy. So for Diamond Joe, we've mapped the eastern third of it. So the image got a bit reduced here in this scan here. But it's effectively a composite pluton where you have an outer equigranular granodiorite, an inner porphyritic quartz monzonite, and an innermost quartz monzonite porphyry as the 3 main phases. Roughly, it's 73 MA. There's a lot of kind of noise in the published ages on it so far, but we're trying to refine that currently. And additionally, I'll just point out that Hervé Rizzo's students are getting to map the western 2/3 of it in some pretty gnarly country. Bell Copper in 2020 staked a fair bit of land in the middle of Big Sandy Valley out here, about 17 kilometers away, 13 kilometers northeast of the Diamond Joe Pluton here. They drilled a hole, I think in late 2020, early 2021, that intercepted a porphyry with an overlapping uranium lead age to Diamond Joe, and they've continued to drill out holes that have kept getting seemingly closer and closer to what could be the heart of a porphyry system. Their best hole hit a leached cap and then hits about 200 meters of, I think 200 meters of 0.4% in a enrichment blanket. If you look at the state geologic map, there is this is the outline of this major pluton here, which is occasionally called Devil's Canyon or Shannon Basin. When you actually walk out here, this pluton does not exist. And instead, what you have is a series of quartz monzonite porphyry dikes that are cutting through here, and then locally, a lot of Proterozoic geology, actually, where this Cretaceous pluton should be. There is, porphyry-style alteration mineralization out here. It's been drilled. It's been called the Roberto or Devil's Canyon prospect before, but this pluton is not present at the modern surface. Lastly, for the other porphyry occurrence, we have the small quartz, Wickiup quartz monzonite to monzonite stock. This has a uranium lead age of around 69. Additionally, there are a number of monzonite and monzonite porphyries dikes out here and an abundance of other dike types as well. There's about 5 or 6 that you can see at the different colors here. Locally, there's weak potassic alteration and principally sericitic alteration. A decent amount of copper oxide on the southernmost margin of the pluton, but otherwise it doesn't look too exciting when you're walking over it.
Carson, before you go any further, could you ask the people who are following this remotely to mute themselves, because I guess some of them.
Please mute yourself online. So we're back to that schematic map of the Big Sandy Valley here, and this is modified from a similar figure that Brian will show in a little bit. Effectively, this has a weird geometry in the basin. When you're on the eastern half of the basin, the Tule Wash sediments dip to the east-northeast. When you're on the western half of the basin, the Tule Wash sediments dip to the west-southwest. So you have this big, effectively anticlinal full geometry at the largest scale here. So we're going to look at a cross-section through here that has some constraints from reality. It's controlled by drill core for at least major structures and lithologies, but it is still effectively schematic in detail. So here, if we're going to move from west to east, so left to right, we have the Diamond Joe Pluton, and you project it up in the air until it would hit this low-angle Hualapai normal fault. I should have mentioned earlier, the big thing with the Hualapai normal fault here is it's very poorly exposed despite being well imaged in seismic. There's one occurrence of a higher angle structure that could be a long strike continuation near Wickiup, and there's 2 occurrences further north that could be exposures of the fault, but we are frankly hesitant about that. Our general interpretation is it's largely buried by the Big Sandy Formation and possibly even by Tule Wash. So we have the Hualapai normal fault. It's buried by the brown Big Sandy right there. And then projecting downward, it would cut an offset and drop down the top of the Diamond Joe Pluton at depth under Big Sandy Valley. And what Bell Copper has been drilling for has been basically the faulted off porphyry system that would have set above everything here. So the caveats I should mention here, the drill holes that are shown here, we only have broad lithologies to constrain here, so we at least know the rough rock type. The bedding to core axis angles for any of these beds, that's a cartoon, that's not real, so don't believe that. And then additionally, the west dipping structures here, these faults that we have mapped in the eastern side of the valley, we do not know their relative relationship to the low angle normal fault, as in who cuts what and what timing. Nor do we actually understand fully what their geometry is at depth there. We have a lot of conflicting interpretations internally. So one model here is that basically all these belong to one single fault system. So you have the antithetic west dipping faults that basically soul into the low angle Hualapai detachment. And as they extend, you get a little bit of constriction in the upper plate and get that nice full geometry. That's a possibility. You could have the west dipping faults be younger and they offset and cut the Hualapai low angle fault. That's possible. And you could also effectively have something that looks identical to the first one, except that the west dipping faults are older, and so they would have been cut and offset somewhere way up in the surface, not shown because they're up in the air. So we know this is the rough geometry, but we don't have a clear idea about exactly what's going on here. But roughly, this is the broad architecture, and the details are still to be worked out here. One thing we have been doing is trying thermochronology on some of the Cretaceous rocks to figure out what's the relative timing of exhumation. When do these rocks come to the surface? As one proxy of basically deciding when did slip occur. And broadly, for those of you that might not be familiar, thermochronology tracks exhumation from depth to the surface. So if you have a crustal column like this, your rocks that are stratigraphically high would get to the surface first. They would have an older age compared to rocks that are deeper that would take longer to make it to the surface. And it's all based on basically passing through different cooling windows and tracking basically when closure temperature would happen for an apatite or zircon in different mineral systems. Basic takeaway though, shallow rocks should have older ages because they get to the surface first in extensional environments. Deeper rocks should have younger ages. So we've done this for a number of the plutons, but we're only going to focus on Diamond Joe here and the dacitic dike in the Aquarius Mountains. And the reason for that is it's a nice contrast for what's the interpreted footwall at Diamond Joe in the footwall of this low angle fault, and then what's the interpreted hanging wall at the Aquarius dike here. Broadly, they have similar uranium lead ages, roughly 72 for Diamond Joe, 73 for the dacitic dike. We're walking now here from things that have a higher closure temperature, meaning they capture things at greater depth, to shallower as we go down these lists. Zircon helium, which captures things at 5 to 7 kilometers roughly, We have single crystal ages that roughly say it cooled between 41 and 24. You can take a weighted mean and say, okay, that one passed through at 21 for zircons and Diamond Joe. Apatite fission track central age of 10.3, plus or minus 1.7. And apatite helium ages that range from 12.9 to 10.9. And a first quartile date that works out at about 11 MA, but it's still, I need to finish the math on that. Compared that to the Aquarius Mountains, 73 MA crystallization age. The weighted mean age for all the zircons is actually basically right on top of that, 74.3. And then the ages for the apatite helium range from 75 to 39, but really they sit at about 61.2 if you take the weighted error. So that intruded really high into the crust. It passed through all those windows really quickly, and it must have been much higher compared to Diamond Joe. So broadly, what I think that looks like is something like this. So if you take this first little cross-section I showed up here in the bottom, and you just cut it up and restore it, you broadly get something with this sort of architecture. So the blue line here is the Wallapai low-angle normal fault, right over there. The brown lines are the small west-dipping normal faults. The black lines are the exposed modern surface from the cross-sections. And then the blue lines are the interpreted Miocene unconformity at depth, basically beneath Big Sandy Valley. And what you get, if you plot up where those samples are taken from, you have Diamond Joe down here, which is roughly at 7 kilometers paleo depth. Whereas the sample from the Aquarius Mountains was something at about 2 kilometers paleo depth. So you had one that was very highly emplaced, one very deep, so it had more time to track these different cooling events. So Diamond Joe at 7 kilometers. Additionally, with Hervé Rizzo, we've been dating some of the Lamperfier dikes at Diamond Joe. They have been dated now at 22 MA roughly, which overlaps very well with the 23 MA zircon helium age. So that could just be a clean thermal resetting event. So that just wipes the slate clean at that point. We have that really, we have 2 largely overlapping ages for the apatite fission track and apatite helium ages at 10.3 plus or minus 1.7 and roughly 11. And if you model them through things like Hefty, you effectively get really rapid exhumation sometime between 20 and 10, but it looks like it's really taking off between 10 and 15 to 10. So this might be my last slide, maybe one more. Additionally, with Diamond Joe, some of the best mineralization that we see there is largely in the southwestern third of the Pluton or so. And that's things like the Leviathan copper, Molly copper vein, the Silver Trails vein, and which is a bit more towards the center of the Pluton. But those would plot roughly 1.5 to 2.5 kilometers beneath where I've drawn a porphyry system for the Big Sandy prospect. When you get to the the eastern 2/3 of the Pluton, oh, sorry, wrong direction. You have alteration, but you don't really see any mineralization anymore. So that's suggesting maybe you're getting out of that system, you're getting much deeper, and you basically could redraw how that porphyry system looks to kind of account for that. So effectively, if you just make that a bigger system, you can explain why we have mineralization over here, but we see pretty barren rocks farther down. And that's just a function of depth and a tilted profile. So with that, I'll hand it over to Brian.
Okay. 3 hands. Thank you. That was amazing. I'm still processing that. Can you guys hear me okay? Okay, great. Okay, I'm going to talk about the Tule Wash Formation and the overlying Big Sandy Formation and then some of the younger units. So let's just dive right in. Okay, so again, Big Sandy Valley, we start with the work by Worley and Scarborough in the 1970s. They did a patch work of stratigraphic reconstruction and mapping in a small patch on the eastern side of the basin, and focused largely on beds that are within the Tule Wash area. Since then, we've mapped north and south and east of there. We've extended a lot of the facies that they've mapped, we've found those north and south and east and west, and so this is part of what Carson was showing earlier. And we've identified also what Worley identified. You have gypsiferous mud facies, limestone, sandstone conglomerate, rock avalanche breccia, and some punctuated by tuff and basalt. At least part of this is coeval with volcanic rocks in the westernmost Kaiser Spring area. It's not necessarily implicit or explicit of that volcanic field, but it's just in that same space in the southern part of the basin. They overlap in space and in time, but we're still working out the kinks of exactly how they relate to each other. But the take-home message is that those volcanic rocks are coeval with the Tule basin fill deposits. The Tule is tilted, it's faulted, and it's a little bit enigmatic about these overall anticlinal basin architecture, but to Carson's point, yes, the beds on the east side dip towards the east, and the west side, they dip towards the west. Most of the basin exposures of the Tule beds dip to the west until you get close to the eastern part of the margin, and then they dip pretty prominently to the east. And at least two major faults and a bunch of subsidiary faults are at least creating this accommodation space for the Tule beds. Let me back up a second. The cross-section on the bottom is a variation on what Carson and I have tried to kind of put together. It's based on the mapping over the last couple of years. So the architecture is still roughly the same. You have a major west side fault that's dipping to the east, and then a couple of major faults on the east side that are dropping the Tule down and dipping them against west-dipping faults. The end of Tule is marked by an everywhere erosional event with an angular unconformity with younger sediments. And so that at least tells you that tilting and deformation happened in a fairly short period of time after roughly 10 million. All right, well, I can introduce a few slides about just the different lithofacies of the Tule. This is one of the ones that Worley mapped in the 70s. It's a carbonate, it's a limestone, it's got red chert throughout. It's about 30 or so meters thick. It has very few fossils in it, but it does have lots of oncoids and piezoids, and it's definitely some kind of a shallow lacustrine system. The map on the bottom is, let me see if I get this right, is from Big Sandy Valley off to the east. You'll see the blue and variations are basalt interbedded with limestone, and they're fairly high in the landscape, roughly 1,200 meters, so about 700 meters above the valley floor, and they've been faulted down to the west against that major eastbounding Aquarius fault. There's also a muddy facies. It's gypsiferous, it has anhydrite, and I should back up and mention that through the mapping, we did identify two subbasins in the Tule, a northern one and a southern one. So we'll come back to that later. There you go. Most of it is selenite gypsum. It's just secondary gypsum. And the clays are generally red, brown, and green, so probably locally derived clays, but very rarely is it laminated. And it's intercalated with other facies. So you see these muddy facies interbedded with limestone as well as some sandstone and occasionally conglomerate. So this is a pretty spectacular area where Worley mapped. It's this is Tule Wash and Burr Wash, Big Wash. They all are kind of closely packed on the eastern side of the basin. Really beautiful, striking lithologies in contrast to each other. So here you have, I'm standing on limestone and then looking up section into gypsum beds overlain by basalt and then tuff and then quite a bit of sandstone. So all in one area. And further up this wash, this is looking east, there has to be one or more faults. We have mapped those, so this is pretty straightforward. There's a sand-dominated facies. This is probably the second most voluminous facies of the Tule beds. It's pretty extensive in that area. This is also in the area that Worley mapped. The exposures are really striking, and they're fairly thick. There's not a lot of deformation other than the tilting, but it's definitely worth mentioning that we don't see any kind of fanning dips. The beds are all coplanar and planar tabular, so there's no, like, we think that there's extension going on at Thule time, but we really don't see evidence for it. This facies is also interbedded with all the other facies I mentioned earlier, the limestone, gypsum beds. And we are still trying to figure out, you know, when we think of a sand or a limestone or a carbonate, we still don't have a really strong idea of where they are in the section. Is it the lower part or the upper part or the middle part? I think Worley struggled with that and tried to break it into formations, but Brad Johnson and I worked on this mostly, and we could not recreate that stratigraphy. So based on that, we kind of backed off a little bit and proposed informally the Thule Wash Formation as one sequence of basin fill rather than 2 or 3. It's too chopped up, and there are a lot of poor exposures. These are spectacular photos, but in most places it's concealed and difficult to reconstruct the stratigraphy. There are interbedded ashes in this facies, 13, I think there's an 11 and then a 10 MA. So we do have an idea of roughly how old they are. And it's kind of comical to try and come up with a clear stereo net of bedding planes. So this is Brad Johnson's attempt in one area. You know, in the photo it looks pretty straightforward, but when you start to really put together all your strike and dips, it's pretty crazy. So we are still in the process of bending these appropriately in pockets or zones within the basin. In general, you can see a little bit of a northwest-southeast trend, but they, like as Carson mentioned, there are a lot of west dipping and east dipping beds across the basin, so if you put them all together, you're going to get a plot like this. There's also a red bed facies. This was also discussed at Tim Marsh's AGS presentation, I think, last year. This is near Tom Brown Canyon, where Knight Creek and Big Sandy and Trout Creek merged together. It's a pretty spectacular place. And not too far from this, like a stone's throw across Big Sandy River, where Cane Springs crosses this same stratigraphy. This is looking to the south, so these beds are dipping towards the Wallapai Mountains. But the imbrication is coming from the Wallapai. So the clasts are coming at least 10, 11, 12 kilometers across the basin into this area. I'll talk about in the next slide a little bit about Trout Creek and the provenance associated with these rocks and where they're coming from. In a large extent, these are really autochthonous. They're in situ, they're in place. They haven't been moved very far other than how far the fault has displaced them in stratigraphic throw. So they're pretty much in place. Iron manganese coating of the clast is really common. And I would suspect that groundwater is the likely culprit for a lot of this oxidation. I can explain that in a little bit. The conglomeratic facies, this is probably the most voluminous part of the Thule beds. There's a lot of conglomerate. Again, another nice exposure, but in most places it's concealed or it's slope wash with float. But we relied heavily on the basin field geologists relied heavily on the bedrock mappers in terms of like, hey, where's this clast from? I don't know. I'm not mapping the bedrock. I'm mapping the basin fill. So we relied heavily on their help to identify these clasts. This one in particular right here is quite an abundant type. This is the Wheeler porphyry, and we see a lot of this in this part of the Thule beds. So that rough color in the upper section of the cliff these are mostly derived from the Wallapais. But the lower part of this cliff face, this is in the same area where Knight Creek and Big Sandy meet together. These clasts are almost 80 to 90% volcaniclastic. So this is derived from a different volcanic field in the upper Trout Creek watershed, but during Thule time. So that tells you that Trout Creek is already part of this depositional system. And this is from a volcanic field that was, I think, 25 to 23, 22 MA volcanics. And so they're being eroded and transported into this basin from upper Trout Creek, which is kind of cool because when you look at one face, you're looking at two different depositional regimes that are mixing. So it's a broad mixing zone within the basin. and I'm probably going to just show you everything I just said, because I forgot about this. There's a lot of conglomerate in the basin, so this is one photo on the east side of the basin. So there are quite a few others. Most of the time, the clasts are non-unique because there's so much other basement and crystalline rocks that are older than the Wheeler porphyry that you can't tell them apart between the Aquarius and the Wallapies. So some of them are non-unique in that regard, but if you're lucky, you might see one or two clasts that are quite unique. Some of the boulders, when you're driving along Highway 93, they're pretty large, up to 8, 9, 10 meters. So that's really impressive. We'll talk about that in a second. And a lag is probably the most common characteristic when you're hiking out there, you're driving down the highway, you're going to see a lag of boulders without any kind of context or cliff face to put them in. And then just to further clarify that in terms of provenance, we have been able to successfully identify, hey, this is from Trout Creek, this is from the Wallapai Mountains, this is from the Aquarius side, and in the southernmost basin, you can say, oh, this is from the Poche Mountains. So in that sense, it's been pretty successful in terms of trying to sort the provenance of these clasts. And then lastly, one other unique characteristic of this facies is they're punctuated by these dramatic, pretty characteristic rock avalanche debris flows. All right. Well, I don't know what Carson's thinking in this photo, but every time I see this photo, I'm reminded of what every single one of us did in the field. We just stared at these outcrops. And I think on the field trip that's coming up in a couple weeks, you'll still even find us that have mapped it staring at them again, because they're quite perplexing. So this is what we've coined the rock avalanche debris flow, but we would also refer to them for a long period of time called a coherent or incoherent breccia. So let me explain a little bit more about these deposits. They're unique in this regard. They're monolithically zoned, which I'll explain in a second, but they typically have these zoned fields of distinct rock types, all granite, all granodiorite, all gneiss, all porphyry, some variation on that theme. They're pretty thick, anywhere between 2 and about 50 plus meters thick. And you can trace them for several kilometers as an individual bed, but you often lack the context of what's above them and below them. So that still remains enigmatic. Occasionally, if you walk enough, you will find a top and a bottom, and they are interbedded with the fanglomerates from the Thule beds. So that puts them into context. They're part of the basin fill sequence and stratigraphy. The matrix is pulverized bits and pieces of the clast. There isn't much mixing. Occasionally there is, but in general, they're not really well mixed. They're not coherent in the sense that they're a framework breccia, but they have been jostled around a little bit. And if you're lucky, you catch the base, you do see some mixing with the substrate rock, which is pretty cool. That tells you a little bit about some insight into the process of that deposit forming on the landscape. Further down dip, which is in this case to the east, and these photos are taken from the west side of the valley, further towards the east, you do see a little bit more mixing, more fluidity, more different types of deformation internally within the flow and at the base. And again, commonly, they're expressed in the landscape as this lag of boulders, and you really don't have much to put them into context. So this is another outcrop. So I see Brad. I also see myself just staring at the rocks. I did not actually go to this outcrop, but it is quite spectacular. Tim Marsh and Morgan reported this in 2020 in GSA and alluded to this as a rock avalanche deposit. And so we would agree with that. There's all kinds of characteristics of this deposit. You see these weird sort of soft sediment deformation zones or boundaries between these monolithologic rock types. So we see things like granodiorite here is in the darker gray zones, and then the Wheeler Wheeler porphyry here and andesite right there. And then you often see these things. That's one of the things I've seen in other places where you see shearing that's sort of subvertical to, not horizontal, but mostly subvertical. And I think that's a characteristic of the internal properties of these flows. There's a rock hammer on the left for scale. And then right across the wash from the same exposure is a nice fault that's cut across this. But what's even cooler, in this case, you actually do see what it's sitting on, and it's sitting on a conglomerate. And this is part of the Thule conglomerate. And then it's overlain by this rock-avalanche breccia and then subsequently faulted. I think that sort of clicked for me on the 4th visit to that outcrop. On the eastern side of the basin, a little bit farther down gradient, this is more typical what they look like. You don't see those fresh exposures, you just see a string of boulders. And in this case, it's tilted towards the east into the Aquarius Mountains. So you get this string of boulders, but you don't really have any other clear insight into the matrix. There's another place on the eastern side of the basin, and Cal for scale. This one is 100% Wheeler porphyry class types. And again, there's no top or bottom, so it's just sitting there. And it's kind of hard to put it into context, but you put your head down and just get through it and get on to mapping, you'll find, oh, this is part of the Thule basin fill sequence. Okay, so this is our frontispiece on the slide. It's quite a spectacular exposure. It's not too difficult to get to. We're going to try and go here on the field trip. So this is a drone aerial photo because it's kind of difficult to take photos on a steep slope with teddy bear cholla surrounding you. This is a really spectacular outcrop. It's the Thule beds capped and cut across by the Big Sandy Formation. And then we have this contact between Thule sandstone above, and what you can't see below is more Thule beds. There's an ash bed that we dated at 10.4 MA right below this. In fact, part of it is actually caught up in the landslide itself, so you'll see these rip-up clasts in here of ash that's mixed in with the slide. You obviously see, hopefully you do see some folding in here, some recumbent folds and shear zones between them. Other clasts, the quartz porphyry, so we see Wheeler and other types that I'm not sure we've identified yet. And then on the backside, which you can't see over here, there's a nice big 8-meter size clast of the breccia that you saw in the previous photos, but it's actually a clast that's ripped up. So either it's cannibalized from further up in the entrainment process, or it's from an older rock avalanche that's getting incorporated into this one. So this was a nice little rendition that Carson did just to kind of put together individual beds. It was fun, exercise and reconstruction. Again, another perplexed Carson. I hope that would make me feel better. It's got a little bit bright of a photo, but you could see this photo on the left is another one of these clasts that's itself is auto-brecciated. Again, it's probably part of an older flow or part of the original flow from further upstream. So this outcrop is about 11 kilometers east of the Wallapies. So, and it's interbedded with sand. I think for quite a long time we didn't really know where the sand was coming from. It was just bedded planar sand, really thick, hundreds of meters, but we didn't know where it was coming from. And then you see something like this, and then we start to put things together. It's like, okay, well, this is actually coming from the Wallapies. Same wash, maybe a few hundred meters away. There's a little bit more context. So this time we take the drone up and take another flight, and then you just carefully walk the grounds, and you'll see normally what I would have probably originally thought of as just clasts that have fallen from the Big Sandy above and just got stuck on the slope there. They're actually embedded into the outcrop. But it's slope wash, so there's not these great cliff exposures anymore. You're just looking at a line of boulders. And occasionally you'll see windows with the lighting just right. You'll see windows of west-facing recumbent folds in those beds. And when they come down to, like, here's a jeep, you'll see these clasts of boulders of granodiorite. Here's another megabreccia clast. Again, this was probably clicked for me on the third or fourth visit. It's really the first time out there, we really didn't know what we were looking at. And this was not documented by Worley, so we had to kind of come up with some, I guess, a lot of ground truthing, really, a lot of walking to piece this stuff together. Okay, so this is further south in the basin. This is towards Wickiup. In fact, it's just east of Wickiup. The geologic map on the left, and then green is this blob of breccia that when we first mapped it, we didn't really have much context for it. We didn't know if it was bedrock. We didn't know what it was. And now, I think with hindsight 2020, I would argue that these are rock avalanche breccias. They occupy a space within the basin bound by major faults. So the accommodation space is there. You never see it in contact with anything else like you do up further north, so we don't have a bottom or a top. But we do have these curious structures as well, these sort of semi-vertical and just odd structural shapes. Yeah, it could be bedrock, but it just doesn't click for me. The other reason why it doesn't click is that you find, in one place, you find, there's a little satchel for scale. It's all granite, and that's about it. And then, there's one or two clasts of porphyry hiding in the granite. So that tells you right away it's mixed. And I don't know how else to interpret this. I don't think it's bedrock when you see one clast that just stands out. That's clearly a tertiary porphyry. The furthest south that we've seen this is actually due to mapping in the Earth MRI area. It's outside of the Big Sandy mapping, but it's down here in the Burrow Creek, right next to the campground. There's a Black Canyon, is just south of the campground in there, and you'll see one of these outcrops. It's this odd-looking breccia, and again, it's 99.5% granite, but there's one or two clasts, I think just one, maybe two, I can't remember, of this rhyolite porphyry right in the middle of it. So I would argue that it's a rock avalanche deposit. And again, there is space for it. There's a fault on the south side up against the Poche Range, and there's lots of volcanics just north of this that are in the subsurface. So space is created for this material to flow into. Okay, so for the timing of the Tule, we've tried to collect enough samples throughout the basin. The sections on the right represent a broad stratigraphic architecture of each of these localities, located on the map on the left, from north to south, 1 to 9, and left to right in the stick diagrams. I realize that it's going to be hard to see the ages, so I'll just point out the fact that we have the youngest age here was at that rock avalanche breccia on top of the ash at 10.4, and the oldest age we have reported is roughly 13.1 in the Pearson Wash area right here, number 2. So of all these sections, we do have some other ages that are a little anomalous. You got a 25 MA above 11 MA, so we're still going to try and figure that out. That's probably inheritance. But in general, 10 to 13, 13 and a half is the age of the Tule beds, with a lot of stratigraphy above and below. The other thing that's worth pointing out here is that in a couple of places up here in the bottleneck quad, we do have a Peach Springs tuff, 18.8. So, but what we don't have is the stratigraphy between the Peach Springs tuff and the Tule beds. So we don't know if basin formation was going on at that time, or if it's just a different period of time pre-Tule Basin. Okay, so to take this home, we think the onset of deposition for the Tule is around 15 MA, possibly 17 million. The depositional axis based on the rock avalanche debris flows is on the far east side, at least 2 subbasins. Paleocurrents are such a great, reliable indicator of of where things are going, and based on these arrows are based on not only just strike and dip, but also paleocurrents. We do have basalt volcanism in the south. And again, I think some of this is slightly interpretive in terms of how these facies would interact with the Kaiser Springs, the westernmost Kaiser Springs area. But again, the space is there. The ages overlap between that volcanic field and these rocks, the Thule. Faulting is most likely coeval, even though we don't see fanning dips or growth faults or anything like that. We don't see any evidence of syn deposition with tectonism. But most likely, there's at depth in the subsurface, there's probably going to be some evidence for that. And following deposition, we know that there's an erosional episode that cut through and eroded quite a bit of material of the Thule. It's so much material that it couldn't have been relocated to a different part of this basin. It's been removed outside of this basin. And this sets the stage for the next basin filling sequence, which is the Big Sandy. All right. So we'll jump into the Big Sandy, and I'll kind of come back to that a little bit because there's enough overlap between those two that we can elaborate on that story about the Thule being deposited, eroded, and then blocked off and filled up again. This formation was originally defined by Shepard and Gooch, 1973, 1972, as muddy facies with carbonates in the southernmost part of the basin. And since then, others, not just us, but there's been some other researchers that have come since Shepard and Gooch, said, hey, well, there's conglomerate, there's sand, they're related to each other, they look like they're the same age. So we ran with that, and based on our mapping, we can actually put together multiple lithofacies. They grade into each other, so it's a classic Miocene basin. It's fairly easy to reconstruct, but we have basalt in the southwestern part of the basin and a red bed facies as well. The green is mud, and it's intermixed with carbonate and limestone in the blue, and then a sandy lithofacies. This blue line right here represents just a couple of outcrops where you see flooding of the basin, where you see a limestone that comes way up into the sandstone facies. So you know that this basin is going in and out of flux depending on the amount of groundwater coming in, surface runoff, that kind of thing. So there's a lot of variability is the take-home message. You see these facies intermixing with each other on a kilometer scale. The paleocurrents show a fairly predictable kind of scenario. The rock types match the rock sources that you see in the Big Sandy. We think it's an alkaline to hyperalkaline setting. We don't really, in fact, I don't think any of us found any microfossils in the Big Sandy. There's only one place we did find it, and it was preserved in a silicified chert bed. It's full of ostracods. But other than that, they've probably been all dissolved. But there are Hemophilian fauna in the southwestern part of the basin. There's a couple of horse quarries just south of Highway 93, and these are in the sandy sort of subaerial beds of this formation. The ages, it's always been a struggle. I don't think we could have probably put in a little bit more effort into refining the ages, but based on ashes within the muddy facies, there's 3 ash beds with a 5.0 to 5.9, a mean age of 5.5, and they did some PMAG on that, but it didn't quite match up, so it's possible that the lower part of the Big Sandy could be as old as 6.7, but as young as 5.6, with still quite a bit of sediment to go above that. We do have a basalt dike and flow on the southwestern side, and we did redate that on an earlier date, and that came out to about 5.2, 5.3 MA. And that's part of the basin that, well, I'll show you a picture of it later. So some of you may have seen this if you're driving at 60 miles an hour or so. These are the road cuts that you first see when you cross over that divide from Burrow Creek Bridge into Big Sandy. And you might see some reddened soil horizons, a couple of cut and fill sequences, and a few faults. But this is the Big Sandy Formation. Further north, this is the Big Sandy Formation sandy facies on top of the Thule Formation sandy facies. And after a while, you do figure it out, but it's frustrating because it's concealed and you may not see dipping, beds that are dipping. But this is definitely the case. And one of the coolest things about the Big Sandy that I think took me the longest to figure out was what this contact does. It's difficult to trace, and eventually it's like, well, it's gone. I don't know where it is. And the outcrops aren't that great. It's sand, and it's not consolidated. So, but it turns out if you go up and down the basin, you see this everywhere. The conglomerate facies does this too. It gets close to the valley axis, and then it dives into the subsurface quite steeply. And so this is a paleo valley that it's filling up. This is the paleo valley that was eroded into the Thule beds and then backfilled with the Big Sandy when it closed itself back up and aggraded. All right, and further south in the sort of the larger subbasin of this, you see the lime and carbonate intermixed with each other. It's beautiful exposures, beautiful outcrops. Here's a limestone that is draped on top of a rock-avalanche breccia in the south. There's another locality of this rock-avalanche breccia on the left, and then carbonate draping up on a paleotopography that's eroded and formed on top of older deposits. So the interpretation that we finally concluded, or at least settled on, was that the lower deposits are Thule age rock-avalanche breccia. There's all kinds of curious features, but a lot of trace fossils, reed mats on the left, burrows on the right, and quite a really pervasive and ubiquitous texture of charophytes and reeds. A lot of gas in this system. So most likely spring-fed carbonates, but hard to tell because a lot of the stuff has been altered a little bit. The muddy lithofacies is also the source of the smectite and illite clays, where the lithium deposits are currently being explored. And so this is also one of the other places we'll look at on the field trip. Beautiful, striking badlands, and some of it's even karst-related topography. On the very southwestern part of the basin, there are red beds. So these are iron oxides again, but not part of the Thule. They're part of the Big Sandy. And this is south and west of Wickiup. This is a geologic map from, I think this is the Aubrey Peak Quad. And it's highlighting these purple polygons on the map. So these are a series of small exposures of basalt that have cross-cut the Big Sandy and then made it to the surface and erupted onto alluvial fans at that time. So the next slide is a photograph taken here looking to the north. And all of this stuff here out to the river is the Big Sandy Fanglomerate facies, and then punctuated by this dike that's presumably coming up a fault not too far away, and then reaching the surface and flowing out into the landscape. I thought I would just throw this in there because every time I see it, I laugh at the, I guess maybe it's more of an insight into my head, like, okay, well, let's go to Google Earth, let's draw a profile, let's put up all our data points, and then let's see what we come up with. So this is part of the process of not just geologic mapping before, during, or after, but it's just trying to use the data to grasp, okay, what should I expect to see if I draw a profile through here? This profile is just to get a handle on prior to the Big Sandy getting eroded, what is the maximum floor elevation of the basin? And that's really to get at, okay, what did it have to cross over in order to breach and spill and erode? So in this case, we've landed on roughly a 750 meter elevation basin floor prior to it spilling over the Poche Range. Okay, in terms of, so that was a very quick ending to the Big Sandy Formation. We can come back to it later, but the take-home message for that basin fill sequence is that it It was blocked off in the south. After Thule time, it filled up, it spilled over, and now it's integrated with the Bill Williams area. And this is just another exercise in trying to track our Quaternary terraces, Pleistocene terraces in the landscape from old being high and younger to lower elevations. I realize that you can't read most of that, but it's just showing you a profile from north to south along the axis of the basin, from high to low, and then the different ages of Pleistocene deposits that are strathed onto older deposits. Of interest, particularly here, is a QI, we call it QI2, so it's a mid to late Pleistocene terrace. It's a river terrace from the Big Sandy River, and it's unusually thick, anywhere from 20 to 30 meters thick. Usually they're about 10 meters or less, but this one was unusually thick and warranted spending a little bit of funds to get a grasp on the age. So this is one of the places where it's the thickest and deluge wash. Here it's about 35 meters thick or so. And so what we did here was we collected a sample from the base for cosmogenic burial, and then one also from the base for infrared optically stimulated luminescence, IRSL, on feldspars. This is for, because we think it's a little bit older than what OSL would normally be used for, we tried this new approach. And so we're awaiting results to see, you know, how long it took to grade a deposit like this. Okay, Quaternary fault. There's one in the basin thanks to Phil. He found this, we should call it the airplane fault, because he spotted it from an airplane back in 1980s, something like that, a long time ago, and just got around to it a couple years ago. So if you haven't spotted it yet, try. Waited till the lighting was just right to pop up the drone to get a glimpse of this. I drove over it probably 5 times. Didn't even know it was there, but Phil did. And for scale, you could see there's a Jeep right there in the center. And that's where the fault is. I guess I didn't draw it on there. But it's right here's the shadow that's cast all along the Piedmont. And here is a piece of the Big Sandy conglomerate that's faulted into the subsurface. So in that case, we have a couple of pinpoints to know a minimum amount of offset for that. But roughly 2 meters of throw in this picture for a Quaternary fan that has a nice reddened argillic surface that the road is built on, and then roughly 30 meters or so throw in older deposits. Okay, this is the last slide, and it's just sort of a segue to an announcement for the up-and-coming AGS field trip in April. This is going to be April, we don't have the dates on here, April 27th and 28th, which is a Saturday and a Sunday. And our goal is to visit the southern part of the basin and the middle to northern parts of the basin, either day 1 or day 2. We're not really sure yet. We have to get an idea of how many people are coming, but we do have 22 registrants signed up. 25 is the capacity, and we're thinking of staying one night over here in the Burrow Creek Campground, and then one night somewhere over here in the middle of the basin. With that, thank you. Yeah.
If you have questions, I think they set the microphone up over there, and because we have people following us remotely, you really do need to speak into the mic.
Mike, how do we tell if someone has a chat on? Okay. Okay.
Doesn't look like anything from.
Okay. Yeah, and if you don't want to walk over to the mic, you can ask me and I can repeat the question, but it's, yes.
So the avalanche, explain to us kind of the mechanism, how you saw that forming, and why
Oh, how it,
breccia bodies just isolated within.
oh, okay. So the question is, how did we come to figure out the relationship between the rock avalanche breccia and the surrounding sand beds? Okay. Oh, mechanism for emplacement? Well, I would think the first thing you need is topography, right, to generate that. So you have to have, we know where the rocks came from. You had to have some topography and slope to generate that kind of runout. I'm not an expert on rock avalanche deposits. I've seen some great YouTube videos on it. The runout distances are quite large, and we have a few cases of paleo rock avalanche deposits in California. They're fairly common. And worldwide, you could see a few good examples on YouTube. I couldn't find one that really fit the Wallapai model, but I'm not surprised to have a run out of 10 or 12 kilometers distance. You know, things, you know, I really can't say. I'm not an expert on it, though. Yep. But it seems clear to me that you know, when it's underlain and overlain by sediment that's sourced from the same area, this stuff has not been transported far. It's in situ, so it's faulted, but it hasn't moved since it was deposited. Does that help answer your question? Okay. Okay. Yes.
Do you picture the rock avalanche deposits coming off fault scarps or back tilted fault blocks?
Oh, yeah.
I'll repeat the question. So, do you picture these rock avalanche deposits coming off of fault scarps, active fault scarps, or tilted fault blocks where things are just coming, you know, parallel to bedding or what have you?
I'm not really sure. I mean, the rock types are bedrock rocks, right? So they're coming from up in the bedrock domain. And yeah, maybe there's a fault in there. Maybe there's a fault that's more basinward. Either case that I think seismogenically generated potential is there, but I'm just guessing. And I don't think these are originating from basin fill deposits that are back tilted and then they're getting incorporated in. We don't see any evidence of mixing of the basin fill within these deposits. They're almost all bedrock dominated. Yep. Oh, Mike, yeah.
Since
Be
no
happy to
one will
give
get
this-
up and talk into the microphone, I'll just bring it around.
Do you have any idea what the lateral spread of these rock avalanches are?
Oh, that's a good question. Yeah, there's a couple places where you can find, either through just the aerial imagery, you can see a color of something that you just mapped, and you'll see it cross a wash, maybe 2 washes. So the most we've been able to trace them is about 5 or 6 kilometers wide. Yep. And obviously this is faulted in a sort of a domino style, so tracing them lengthwise, longitudinally is not possible. Yep.
Brian, a question for you. This seems to me like an extraordinarily complex sort of basin analysis. Is this pretty typical of the basins here in the central Arizona and up into the western Arizona?
I don't think it is. I think when I first came into Big Sandy, I thought it was just going to be another basin. You know, and you'd see the Big Sandy formation, you're like, oh, that's cute, there's some nice clays and stuff. I had no idea that there was a whole nother sequence of basin fill, really, until we started doing research ahead of the mapping campaign. And then at that point, it took probably a year of just like, okay, so these rocks are, this older basin fill sequence is from the same basin. Now we got 2 different stories. And that part is not typical, either because we're biased by not seeing as much exposure as we do in Big Sandy. It's well exposed, it's dissected, and not a lot of other basins are dissected as much as this one is. So I'm not sure. This may be characteristic of some other set of basins, but not for all of them. I think what makes this one unique and cool is that it's two different sequences of basin fill punctuated by erosion and then backfilled again with a second basin fill sequence. So that's pretty neat. I don't know of any other place like that. Oh, yeah.
Do you have any constraints on the age of the supergene, the enrichment, and the leaching that's with the deposit, the porphyry?
No.
Do you have any sense is the blanket inclined or is it flat?
It has been pierced by exactly one hole. If there was a second hole, we could probably make it more of that arm dance here. If you look at my restored cross section, effectively that supergene blanket would be at the modern or the Miocene surface. If you look at Tim's cross section through, which I don't have, you can just leave it here. Yeah. If you look at his cross section through the Big Sandy prospect, that's been part of his talks, he does show that the basin fill is kind of dropping off towards the northwest, but you would have to hit it in another hole elsewhere to kind of confirm that it is tilted modernly. But it is something to be worked out at some point. Yeah.
Yeah, Brian, maybe touching on Mike's question and potentially that last slide, do you have any ideas based on the mapping or other ideas for, what dammed this valley and then what might have caused it to breach the dam and then dam again, for these multiple generations of basin fill?
Yeah, I thought I had a slide in here that had a little bit more of a close-up on this southern volcanic field. And there the ages are 11, 10 MA. So that's squarely within the time frame, or at least overlaps partially with the Thule deposition. And so there is an older conglomerate at the base of those lava flows that has southeast imbrication. So the inference there is that you had some gravels exiting the basin towards the east, and that would have been that erosional episode. The timing's roughly right. And so the damming mechanism would have been the bimodal basalt and rhyolite domes in that southern part of the basin. Yep.
Is that for the Thule specifically? And then what about the Big Sandy?
Yeah, that would have occupied an erosional paleo valley cut into the Thule, and after those lava flows were deposited, the Big Sandy covers that up. That's what we mapped. Yep.
Thank you.
Okay.
Anybody else? Any other questions before we let Carson and Brian go for the evening? And we've got a few minutes, like 15 or 20 minutes before we have to really be out of here, so there might be an opportunity to chat with them about the field trip a little bit too. Thank you guys so much for doing this. It was a great talk, and it's going to be a marvelous field trip. Oh, we've got an online question. Can you?
Okay.
I think they can pull them up on the monitor.
Yeah. Mike, can you hear me?
I hear you, Dan. That's Dan Aiken.
Yeah. I was just wondering if, in some ways, with the monolithologic breccias, this seems like a kind of a younger version of the locomotive phanglomerate, where there's, for example, the Chico-Shuni, which is the Precambrian, and then there's different packets of Laramide intrusions that are associated with the Ajo deposit. It seems that, based on your explanation, that the Big Sandy area is analogous in some ways. What do you think?
I'm not familiar with the locomotive area, but we did a little bit of research, and they're all over the Basin Range. I mean, the nearest ones are in the artilleries just to the south. And there was a great paper done in the 90s about those, the mechanisms, how they worked, and they had really good exposures in context. And they're described the same way, monolithologically zoned autobreccias. So that's the nearest, closest proxy, but there are many other places in Winkleman and well, I say many other places, but it's based on my limited knowledge. So I'm not familiar with the locomotive, but I'm not surprised that there are going to be a handful of other places in the Basin and Range that host these.
With your studies, do you have a sense of what the actual vertical might have been that drove I guess gravity would be a huge component, maybe water, but what would be the vertical dimension in these failures that would cause them to flow out 10 kilometers? Are we talking like thousands of feet of vertical?
That's a good question. Gosh, I wouldn't know really how to answer that. I would probably argue that 1 degree slope is enough. I mean, you can get amazing runouts with a very little topographic relief, depending on the material. And my understanding is I'm sure someone's got the code word for this, but these are acoustically functional runout flows. So there's some amount of acoustics and fluidization involved in these runouts. It seems like the toes of these flows are a little bit more fluid. You see more mixing on the eastern side than you do on the western side, but that's not a rule of thumb. I'll admit we just touched the surface by documenting that these exist, and we plotted them on the map. But beyond that, we're really just putting them into the stratigraphic architecture. I think this area would be a great place for future research to go in to these places, map them in more detail, because there are a lot more of these that we missed. I'm sure of it. Yes.
Okay, thank you so much. Great talk.
Dan, this is Phil Perthree. I would just comment, the Wallapies, there's actually, even today, there's a lot of topographic relief in the Wallapies. And there's no reason to think it wouldn't have been more. I mean, the active faulting along there is 10 million years old. So I suspect the mountains were quite a bit higher. And even though these things can run out, they typically start on some pretty steep terrain and then they do run out. So I think that's probably what's going on.
And, Brian, Emily Kunkel has a question for you and for Carson. Here it is. What is your leading theory about the timing of the anesthetic faults on the eastern side of Big Sandy? Do you think at depth they could be syn-extensional with Thule and you could see growth strata in Thule at depth? Asking because maybe we see growth strata in seismic. Not sure though.
Yeah, if you see growth strata in seismic, then great. I don't think we've gotten that far yet. We've seen the seismic, but it doesn't seem super obvious that you have fanning dips. Growth strata is a term I would probably use more for something in the Gulf of Mexico, but maybe not out here. I think Carson and I and others probably suspect that you're going to have some sort of fanning dip relationship. I don't know how you can have syn-extensional deformation at the older part of the Thule beds, but you have planar beds of the Thule that have no indication for fanning dips whatsoever at 10 million years. So what's remarkable about that is that all that tilting is accommodated after 10 million, but before the Big Sandy occupies that space again at roughly, well, we don't know, so let's just say 6 million. So between 10 or 9 and 6-ish, there's quite a bit of antithetic deformation, at least on the eastern side of the basin. That's my stab at that. Carson conveniently has gotten occupied in a conversation, so. It's a good question. We've thought about that a lot, and I think that's still to be determined how to restore these cross-sections. On the field trip, we have about maybe 15 or so cross-sections that are undeveloped. but we'd like to put them out there underneath magnets on the vans in the field trip. It'd be a great place to talk about this. One more mic, I think. No?
Oh, hang on.
Oh, yeah. Thanks for hanging in there.
Okay, EC. All right, here's the question from EC. At Bell Copper's Big Sandy property, BS1 hit a very small intersection, 2 meters of the enrichment blanket, chalcocite, so BS1 and BS3 could be tied together 1.6 kilometers apart. One question, do you think the hanging wall that is moved potentially 13 kilometers is intact, or is it too hard to say with it being undercover?
Oh, oh yeah.
I would, we've mapped a number of faults that deform the Tule Wash sediments on the eastern side. Those are all west dipping faults that if you project them at depth, you would likely have, fairly chopped up hanging wall strata there. So, frankly, it creates, this is Brian's interpretation. I had a slightly simpler model. But yeah, so in here, I only show 2 of the faults, but we have many faults in the Tule Wash formation that are west dipping up here. And so it creates the possibility you've possibly folded that system up several more times. And if anything, that creates more exploration opportunities.
Yeah, and I'll add to that that in the area where those wells were drilled, you have the basin fill has facies derived from Trout Creek, which is right there. So that watershed is really unique, and having basin fill that's derived from that watershed means that those rocks have not moved very far. Certainly not 13 kilometers from the west. You can't have Trout Creek all the way on the west side of the basin and then fault it over right to the mouth of Trout Creek today. So I don't know if that bears on the same question, but that was just in my mind.
It is 7:50, so we'll have to be out of here in just a couple more minutes. So if there's any last questions, otherwise, thank you guys so much for doing this. It was a great talk.
Thank you.